worry with because I'll have blanks in that equation. And Maria did this. Notice he just talks about some of these energy changes, which again, that's all part of nuclear chemistry, but it's not the part of nuclear chemistry we're interested in. There's the terminology. What's next? Transuranium elements. Sorry about that. There's our bombardment reaction. I showed you the short way of representing that. And remember, that's not uranium over here. For people that learned the lecture, that's EV on our modern periodic tables. In the old days, we just put an X there because we didn't know what to call it. Okay, this is a brief discussion of nuclear stability. And as I said, there are about 3,000 nuclides people have discovered. Most of them are radioactive, a few of them are stable. And when they start looking at it, they find that there are certain magic numbers in the nucleus. Just like in chemistry we do the octet, electrons always want to get to the octet configuration. These are what they call magic numbers for protons and neutrons. Notice a lot of them are duplicates, but here you have a lot more numbers. You don't have this one. So and if this were a course in nuclear chemistry, or if this was 75 or 30% of your grade, I'd say learn this. And notice something like helium that has 2 protons and 2 neutrons, they call that, yes, doubly magic. What could be easier? So when they talk about double magic, it means it has the same. It has one of the magic numbers for the protons and one of the magic numbers for the neutrons. There are only a few things that are doubly magic, obviously. But this takes care of the magic numbers. Let's go to the next thing. Here's what they find. First of all, you add this up. That's how many stable nuclides there are. If the atomic number and the mass number are both even, there are 163 stable nuclides. If one's even and odd, or odd and even, there's a third of that. And ones that are odd for both numbers, there are only about 4 of them. All the other nuclides are radioactively unstable, meaning they undergo radioactive transitions and decay. And I already mentioned bismuth 209. Anything above bismuth 209, higher atomic mass number, or higher mass number, is going to be radioactive. Those are things, just little facts you want to keep in mind. Here's the so-called band of stability. What he's plotting is the proton. He calls it proton number here. Most of the time we just call it atomic number. And in 1A I always say it's much more descriptive to call it proton number, but they want to keep the students a little bit mystified, so they call it atomic number. But it's really the number of protons. And here he plotted the number of neutrons. Notice here's the 50-50 line, and it sort of swings up this way for stability. This is called the band of stability. Notice we have a nuclide up here. We can get to here. It doesn't go up. It can go down and over, or it can go like this, depending on the different particles. And in fact, what he says right here, if you're on this side, positron emission will take you closer to this. Electron capture, which is equivalent, takes you closer to this. If you're on this side, you do beta emission. And up there, what else does it say? Oh, he doesn't say. This is called the band of stability, the belt of stability. And one thing that the old textbooks used to have, way up there at about 140 to 150 neutrons, they used to have a little circle that they call the island of stability. And that's what they were trying to produce with all these bombardment reactions and get up in there, because they figured they could get some really high mass number nuclides that would be relatively stable. And it's disappeared from the modern textbooks. Then I noticed in one of the recent articles they found something way up there that seems, they haven't named it or done anything else with it, but it seems to be stable, and so they may be putting the island of stability back in there at the top. Up there where it says alpha emission, up a little bit above that it used to be. And it may come back. This is just plotting some information that people know about stable nuclides. There's some half-lives, and that's the next thing we want to get to. What the heck are we going to do here? We're going to do genetics.
Yeah.
and he does it for H2O too. I'm just going to write what we did in kinetics. You remember that?
Yep.
What did we call that?
First order.
No, I didn't get to that part yet. You can't tell that's first order. You don't know what I'm going to write next. I did say at the time nuclear decay is first order kinetics, but what did we call this? We called that the rate of reaction. It was the change in A divided by the change in time. In nuclear chemistry, we're going to call this activity. In fact, I'm going to rewrite the equation and put it like this. Instead of talking about the concentration of molecule A, that's what he did there with the hydrogen peroxide, we're going to talk about the change in the number of atoms over delta T. This is the activity. N stands for the number of atoms, or nuclides, because that's just a term. So we're going to call it activity instead of rate. But everything we did before is going to be true. It's going to be delta N, delta T. And it's equal to, and up here we wrote and now we can say it's first order because I put a 1 there. And we call this the rate constant. And we said these are always positive changes, so we'd automatically change the sign. Although one of the problems we did in the homework, you had to leave the sign in so you knew whether you're doing with reactants or products. Okay? But now in nuclear chemistry or radioactivity, you're going to put minus lambda. Guess what this is? The rate constant for decay. We just used a different letter. So it's still the same thing we did before. It's a rate constant. And now we're going to put N to the first power, where this is the number of atoms. Okay? So if we want to do the, I'm going to get rid of that 1. It looks weird. I'm going to get rid of that 1 because you know there has to be a 1 there, otherwise I wouldn't have bothered writing it. Okay? So that's the first thing. So if you know the number of atoms, you know the rate constant, you can calculate the activity. Typically, we ask for activity in disintegrations per second. It's the number of atoms breaking up per second. So delta T is 1 second. We could ask for disintegrations per minute or disintegrations per hour, but they usually say disintegrations per second. So that's that part. So there's the terminology that we use with nuclear chemistry. Then, what we did, and I ignored it when we were back in the kinetics, we did see that he showed us how to calculate the half-life. So what we're going to do is change this to calculus notation. So far, so good. Then I'm going to rearrange this. And you don't have to know this if you don't like calculus or whatever. Because I'm going to give you the answer, and that's all you have to know for this course. But for those of you who may be a little more interested, we just say, I'm going to integrate this. This is the starting number. This is the number at some time later. And this is T starting time, starting number, time sometimes later. And you know that what you get out of this is LNN minus. And if you don't know it, doesn't matter because I'm writing it down. We're just going to use it eventually. And on this side, multiply lambda times 0, you get what? 0. So I'm going to get rid of that. Okay? And then I'm going to do my little sleight of hand, and now you have to know this. That's one of the equations we use. This is one of the equations we use to calculate activity. That's the equation we use to do some of the problems, so I have to know which ones in a minute. And the other thing I'm going to say, half-life. T1 half. That's how we write it. It's when n is 1/2 n0. That was easy. You can say, "No, that's the algebra I can handle," right? Maybe. I don't know. I'm not going to ask you to derive this. I'm just going to get you the result. I'm going to say ln 1/2, and I say, I know that's going to be a negative number, so I'm going to do ln2 plus lambda t 1/2. Right? Because if I have it 1 over 1/2 and it's minus, I change the sign, and now I make it a 2. I have to change the sign on both sides. That was fun. Here's the other equation you need. And they always say, this equation in the book, why did they make you memorize that 0.693? That's the natural log of 2. Which is easier, pushing ln2 and getting a number that you can use in your calculation, or entering 0.293 or 0.6? See, you forgot it already. So you don't want to enter the wrong number. So this is the easy thing, because you have a calculator that does ln's. When I went to school, I keep going back to the old days. I had my log table, but I didn't have a natural log table because we didn't have to buy one. Then I had to figure out how to convert from natural logs to log 10. So instead of doing that, we memorized 0.693. But you don't have to do that unless you really want to. So now I've given you the 3 equations you need to do any nuclear chemistry problem. You don't have to worry about this. I'm not going to ask you to do that. I did the derivation for you, but this was easy. I'm going to get rid of that. And get rid of that. Okay. Let's watch him do it. What? You want to watch him do it? I go fast. There he goes. He's integrating. Doing that. There's the equation I had, except he's doing in terms of concentration of A, because he's going back to chapter 14 or 15, wherever we saw that. Don't worry about that other equation. We don't write it like that. We've got all the equations we need. There he does this. Minus ln2, because he changed, he put the extra step in there. I just said you know that. So he did it. And he does this. T1 half ln k, and then he wrote 0.693. So there you go. So there's everything. Now, when we talk about radiocarbon dating, I'm not ready to do that. I want to do a problem. He has a problem. Nope, he doesn't have a problem. That's okay.